Hello, everyone. My name is Bruce. I am the founder of the Killarney Provincial Park Observatory, and I'd like to give you a presentation that I typically give visitors to the park. I usually do it from the beach, but sometimes I do it in the amphitheater as well. It hits on a very interesting theme that's near and dear to my heart, and I hope you enjoy it as much as I enjoy providing it. So when visitors come up to the park, they definitely appreciate all the rocks and that they see around them. This presentation is on how we can use the rocks and meteorites to understand the Earth, the Moon, and Mars. And we'll use some of the meteorites that exist within Killarney's own collection. Now, I'm not doing this from Killarney. I'm doing this from the comfort of my own home. But these meteorites do exist there, and I brought in pictures of those meteorites into the presentation. Okay, so let's get going. So when people come up to the park, they enjoy the beauty of the rocks, the pinkish granite, the white quartzite in the background, and they really get a fond appreciation for the incredible geology that makes Killarney Park truly special. But if you go to the beach, and this actually is the East Beach or the second beach, you'll see that there's lots and lots of stones, rocks, and pebbles upon the shore. Those rocks, stones, and pebbles tell a story, and they tell an incredible story of how the park came into being, came into existence. So before we go further, what I normally have is I take the audience who's with me and I say, go out, spend the next 10 to 15 minutes, go to the beach, collect a handful of rocks. You're going to have to return them. You can't keep the rocks. But when collecting those rocks, try to choose ones that are as diverse from each other or as different from each other as you possibly can. Color, texture, shininess, jagged, smooth, all kinds of different features. And let's regroup in 10, 15 minutes. 10, 15 minutes later, we do a lab review and let's see what they brought back. Okay, and to do this, we're going to actually help them identify rocks by a chart I put together for a blog article that exists at Ontario Parks Geology. So if you do a Google search on Ontario Parks Geology, you can see this chart and a much more detailed article that myself and Dr. Gordon Osinski wrote a few years ago. Okay, so let's start off with rock identification. Many of you have gone through this, but I approach it in a slightly different perspective. I start with the three basic categorizations, but then I work down to features that help you identify the rock. So does your rock have shiny crystals? You may need a magnifying glass or a loupe to see that. If so, it's probably an igneous rock from the Latin word for fire, formed in magma and cools and crystallizes. Now, some crystallize very quickly because they're ejected from a volcano, and those tend to not have big crystals because they didn't have time to grow. Some crystallize very, very slowly, and that typically occurs in a big magma pool, or what we call pluton, that occurs deep beneath the crust of the Earth. But that can cool very, very slowly, and as a result, the crystals have time to build and build. On top of that, the chemistry behind the rocks may play a role. So if you are looking at some of these rocks, you may see some of the rocks are light. So if you have crystal rocks and they're light, they're called felsic for feldspars and silicates, and they all have quartz. On the other hand, some of the rocks might be dark. They'd be mafic from magnesium and ferrous iron containing. Doesn't help us really with some of the long-term identifications, but does help you understand the chemistry behind it, and at least you know if you're dealing with a light rock or a dark rock. Now in Killarney, crystals that are large in a light rock pretty much guarantees that it's granite. On the other hand, in Killarney, you rarely see it, but it's not impossible to see. You might see large crystals in a dark or mafic rock, and we call that gabbro. If you have small invisible crystals, and these are more common, they are what we call basalt. Some people call them basalt, but more commonly the name is, or phrase is, basalt. And these are rocks that were probably ejected from lava. You find them a lot in Hawaii, and they are rocks that have not had time to form large crystals, so that's why the crystals are small, but they have a high iron content and some magnesium, and that's why they are dark. Okay, so those are the igneous rocks you'll typically find in the Killarney region. Does your rock have grains or small pieces in it? If it does, it typically is sedimentary rock. Rocks that form from the collection of sediment, erosion of existing rocks, collection of minerals from warm shallow seas, or accumulation of dead organisms. And we have several types of sedimentary rocks. If it's from organic material, then I typically would have calcium carbonate within the rock. And if you were to add vinegar to it, and please don't do this on the beach, it would fizz. An example of that is limestone. While not a very common rock in the park, you do find it towards the outskirts as well as towards Georgian Bay. And if you go towards South Georgian Bay, limestone is actually one of the most common rocks you'll find. Another kind of sedimentary rock is composed of varying sizes of small grains, such as silt or sand, etc. And those form various kinds of rock as well. The ones we're going to talk about here are small sandstone grains, sand-sized grain forming sandstone. And if you look at that color, you've probably seen that color before. Think of Tatooine in the movie Star Wars. A lot of sandstone in the background there. Sandstone is a very, very common rock found all over the world. We don't find too much of that at all in Killarney anymore, and we'll soon talk about why. And then finally, if you have sedimentary rock that's composed of sediment of varying small sizes of rock, then you'll typically have one or two types. You'll either have breccia, which we are going to talk about. This is one I found on the beach. Maybe not so hexagonal, but I did find it there. And it's composed of rocks that are angular. And if they're smooth, it's a conglomerate. Angular rocks mean that they must have formed an explosion or a blast or something, and the rocks, as they were exposed and falling back to the ground as sediment. Okay, so that's sedimentary rocks. The last classification we're going to talk about is metamorphic. Metamorphic means to change, meaning change of form occurs when pre-existing rocks are changed from one to another by heating, pressure, or both. If the rock has layering, or what we call foliated, varying degrees of folded layers, then it's gneiss. And there could be other ones called schist as well, but gneiss is the one you typically find. Now, you don't see it too much in Killarney, but you definitely see it towards the town of Killarney more than the park, and definitely in Parry Sound. It's one of the most common rocks you see in Parry Sound is gneiss. Another kind of rock that actually has made Killarney quite famous is another metamorphic rock, and that's the hard white rock we see on the mountains. And that's the rock quartzite. It's not a mineral such as quartz, it's a rock quartzite. Okay, so almost all rocks that we see here you'll actually find in or around Killarney: granite, gabbro, basalt, limestone, not so much sandstone, breccia, rarely, gneiss, rarely, and quartzite a lot, with granite and quartzite being the most common forms that you'll see in the park. Okay, so typically I'll go through this slide with the families and all those who brought back rocks, and let's try to identify their rocks, and that may take another 5 to 10 minutes. So let's talk about the geologic history of Killarney Provincial Park. Why do we have such amazing geology in the park? It's in fact considered one of the crown jewels of the Ontario Provincial Park system for its amazing geology, and one of the most amazing sites anywhere in the world for its incredible geology. So what's the background story? How did this actually occur? Well, to do that, you have to picture a different time. Time is about 3 to 3.5 billion years ago. And at that point in time, a large area of land emerged from the molten lava that was the Earth. And we call that a craton. And one of the first cratons to form was actually just north of the park, and it was the Canadian Shield. So that stretches all the way from Ontario, northern Ontario, through Quebec and over to Newfoundland and Labrador area, primarily Labrador. And that was some of the first solid mass that formed on the Earth. As water was deposited on the Earth, either from comets hitting the Earth or from deep within the process being ejected by volcanoes, those water formed seas and oceans, and eventually a giant ocean or inland sea was forming against the beaches of the ancient Canadian Shield. So 3.5 billion years ago, standing on the shore of the East Beach in Killarney Park, it would have looked like an ocean with waves cresting upon that beach. And these oceans and seas were full of primitive single-celled life eventually, and that life would have deposited and formed sediment. Those seas were also full of rocks, and they were forming rocks, and then they would break down the rocks, and those rocks would be deposited on the beach. A lot of the rocks that would have formed at that time would have been sandstone. And a lot of sand being formed, and over time, the compression of that sand would have created sandstone. Very, very common rock. Now, about 2.5 or so billion years ago, giant geologic forces in the form of tectonic plates were forced upon each other. So you have two different tectonic plates. Sometimes you can have one plate go under another one. We call that subduction. But in this case, you had two tectonic plates who hit each other and then rose up like that, forming giant mountains. And the mountains in Killarney perhaps were as tall as the ones in the Rockies, huge, tall mountains. But over time, those mountains would have been worn down by glaciers. And those glaciers had a big impact on what we see today. But when those mountains were formed, there's a tremendous amount of heat and pressure being exerted on the rock. In this case, it was largely sandstone. Here's the glaciers wearing down the rocks. And as you can see, glaciation plays a big role in flattening everything. Glaciers can be almost 1,000 meters high and can flow for many, many tens or hundreds of kilometers. They would have come down perhaps 2 or 3 times over the last several million years. Okay, so let's see how Killarney's rocks were formed. We had the oceans, and from the oceans, we would have had silt and clay forming shale. We would have had sand, and from the sand, we would have had sandstone. And then from some organic life, we would have had limestone. When the mountain building process occurred, these 3 particular items would have been affected in different ways. The limestone would have continued unabated as it is. The sandstone would have been actually converted into quartzite. So quartzite is actually more and more processes on sandstone. And shale would have first been converted into the rock schist, which then would have been converted into gneiss. And that's how gneiss is formed. The other rock that would have formed would have been a large crystalled igneous rock known as granite. Now, granite would have formed in a pluton, or a big pocket of magma beneath the Earth's crust. But over time, between the mountain building that would have risen up some of that early plutonic material, as well as glaciation that would have taken off the surface layer, a lot of the granite became exposed. If you look at El Capitan in the United States, it is actually a giant pluton of granite that was formed in the same way. Okay, so original rocks, shale, sandstone, limestone, and granite, changed by mountain building or exposed by erosion and glaciation, forming these rocks that we see here today. Okay, let's move on. So that tells you the story of Killarney Provincial Parks. These mountains that we see as the quartzite would have once extended maybe 5 to 6 times taller than they are today, maybe even taller than that. But the granite that we stand on, that Sunset Rock, for example, where this picture was taken, would have actually been a pocket of magma, tens of kilometers thick potentially, lying tens of kilometers beneath the crust that was eventually exposed when the tectonic plates collided to each other and rose up, and then glaciation wore down the top surface layers. So how does all this tie into the understanding of the Earth's history through planetary science and through meteorites? So a long, long time ago, perhaps 4.5, 5 billion years ago, a distant star would have gone supernova. And the shockwave from that star would have probably collided into a gas cloud we call a nebula. That gas cloud would have collapsed into varying stars or forming various stars. And those stars would have had a protoplanetary disk left afterwards. That disk would have been primarily composed of a lot of the material left over from the formation of the solar system and the planets, and leaving a lot of dust behind, as well as icy material in the form of comets. The sun, of course, being at the center. In time, though, some of the material would have eventually collided with one another, forming bigger and bigger objects. And we think at one time there may have been as many as 20 different planets or planetesimals in our solar system, rather than the 8 we typically think of today. Scientists currently believe that 2 ancient planets, one they call Gaia, which is now the Earth, and one they call Theia, which would have been about the size of Mars, collided in this artist's illustration, showing that, forming an entire explosion that would have ejected a lot of material out into space. The lighter material would eventually form the moon. And the lighter material in this case was primarily made of silicates, silicon and oxygenated material. The heavier material from both of these objects, such as nickel and iron, would have formed the core of the Earth. And that's why we think that the Earth is primarily composed of heavier materials and the moon currently is composed of lighter materials. Now, we also still had a lot of the ice floating around us. And this picture taken by Bill Gardner of comet Meteorites. shows one comet that would have come into view from Earth. There are many, many millions, perhaps billions of comets, which are basically icy, dirty snowballs still in the outer reaches of our solar system. When a tug from a nearby star or gravitational influence of Jupiter or Saturn, a large planet, attracts them, they come into the solar system either to orbit the sun or to be thrown off, never to be seen again. But when they come in towards the sun, they start to melt. And when they melt, they give off a lot of dusty material, dust and grit. So here's a picture of the nucleus of a comet. This is the dirty, icy snowball itself, giving off lots of dust and ice and grit behind it. When the dust and ice and grit hits our atmosphere, it burns up, causing what we call meteor. Now, sometimes the material isn't from an icy rock or comet, it's actually left over from the formation of planets, and we call those asteroids. They tend to be much bigger, tend to be much heavier, and sometimes when they burn up in our atmosphere, they don't just stop in the atmosphere, they actually are big enough to hit the ground as what we call a meteorite. Here's a picture of a car being hit by a meteorite. And we do know that at least one person has substantiated evidence to show that she was hit by a meteorite, but obviously it's quite uncommon. Meteorites, however, in the past, especially in the early days of the solar system, were much more impactful. It is believed that the entire Sudbury Basin was actually created by a giant asteroid, or maybe a comet, we're not quite sure, hitting the Earth about 1.8 billion years ago. And it would have carved out a crater, which over time, with plate tectonic activity, stretched into the ellipse that we see as the Sudbury Basin today. So let's talk about the meteorites in Killarney Provincial Park's collection. This one is an iron meteorite currently on loan. And the iron meteorite typically are very, very heavy. If you have a compass or even an iPhone compass and put it next to this iron meteorite, you'll actually see that the needle of north deflects. It doesn't point to north anymore. It actually points a bit more to the meteorite because it contains a high amount of nickel and iron in it that has been magnetized. If you cut the meteorite in half and etch it, you'll see what's called Widmanstätten patterns or Thomson's patterns. Widmanstätten and Thomson are the names of various discoverers of these patterns. And this is occurring because of a rare nickel iron alloy. There's two of them, tannite and chemisite. These alloys do not exist on the Earth and are only found in meteorites. So if you cut a meteorite in half and etch it, and it's an iron meteorite, and it's really a meteorite, not some earth rock, you'll see the Widmanstätten patterns from chemisite and tannite. Another meteorite we have in the collection is very, very rare, and it's called the Allende meteorite. Allende meteorites are carbonaceous chondrites, meaning they have a great deal of carbon in them. They also have a lot of these chondrules. And you also can see these white little bumps here. These are called calcium alumina-rich inclusions. And these calcium alumina-rich inclusions also have isotopes in them that we can measure. And it indicates that the age of the Allende meteorites and meteorites similar to this, carbonaceous chondrites, actually indicates they formed about 30 million years before the Earth did. So these are actually older than any rock you'll touch on our planet. What's even more interesting is if you further study the isotopes, you'll find some strange anomalies. You'll find isotopes that lay in a key signature that we don't see anywhere else, even in our solar system. And it is now believed that this kind of carbonaceous chondrite contains what we call pre-solar grains, grains of dust and grit and material that actually was perhaps from another solar system surrounding another star that went supernova about 70 million years before our sun formed. And who knows, it may have been that star, the shockwave from that supernova that actually hit our molecular cloud that eventually formed our own sun and planets. An even more rare carbonaceous chondrite is called the Aguas Zarcas meteorite. This was found only in 2019, so it's a very, very new meteorite. As such, it's very, very fresh and has a great deal of information to provide us. So in addition to all that we just discovered and mentioned about the Allende meteorite, the Aguas Zarcas meteorite, like some of the other rare ones known as Murchison meteorite, are full of rich carbon material and lots of hydroxyl material and amino acids and even peptides. So it is possible that meteorites like these that we're only seeing today may have, in fact, brought a lot of the organic molecules to Earth that formed the very first life we know on our planet. Let's see a quick slide of some of the history of the Aguas Darkest meteorite. I'm not going to go through all this in detail. You can print out the slide from the PowerPoint presentation, but you can see that somewhere about 7 billion years ago, we think there's an interstellar cloud, pre-solar grains in that interstellar cloud. You can see the molecules that are being visible there. Eventually, the solar system formed about 4.56 billion years ago. The CAIs is the calcium alumina-rich inclusions that we talked about with the Ende meteorite. And then an asteroid formed eventually around our sun, which hit the Earth in 2019. So pretty incredible history of the Aguas Darkest. In a sense, you are touching or seeing something that has its roots back from almost 7 billion years ago. Now, can we use this information to tell us more about the moon? Well, when we look at the moon, and people have been doing this for, of course, many, many thousands of years, you'll immediately notice that there's dark areas and light areas. Hundreds of years ago, people thought the dark areas were filled with water and ocean life because they look bluish. In fact, they gave them the Italian name for sea, which is Maria. That's plural, or mare for singular sea. Here's a zoom in of sea here. And in fact, you may have heard the word sea because the first Apollo landing on the moon, Apollo 11, landed in the Sea of Tranquility, which is this basin here, and it landed right around this area down here. The other areas that we see on the moon are brighter and higher up, and we call these the highlands. And these areas didn't obviously form in the same way, or certainly do not look the same way today. They're heavily, heavily crater laden, and they tend to be brighter, not as dark. Are the clues that we've learned so far with rock identification and meteorites that could help us to uncover some of the stuff we see on the moon? Well, one thing we know is that the seas are darker. And dark meteorites, dark rocks that we see on the Earth tend to be what we call mafic, magnesium ferrous laden, and the ones we typically think of are gabbro and basalt. Whereas the lighter material tends to be more silicates or feldspars and mafic. And that's, of course, if they're igneous rocks. Perhaps some of the moon rocks are different than igneous rocks. Well, it just so happens that in Killarney's collection, we actually have a meteorite that's from the moon. And provided you're very careful with it and keep an eye on it, you can let the park visitors touch this particular meteorite. This meteorite is known as a feldspathic regolith breccia. Breccia, if you remember earlier, we talked about two types of sedimentary rocks, conglomerate and breccia. Breccia are rocks that have jagged edges or angular edges. And regolith means like the surface layer. It's typically like soils on the earth, but it can also be made of dusty material. And feldspathic means it has a lot of feldspars. So in this particular case, we know that this rock came from the highlands because it is light material. Probably was created from repeated impact blasts occurring on the moon, and the resulting ejecta, or the material shot up from the meteorite crater or the asteroid crater on the moon, would have settled to the ground in the form of dust and small bits of rock and grit. Over hundreds of millions or billions of years, the weight of this grit would have compressed the rock, just like we see on the Earth, sedimentary rock, forming a solid material. This one probably came to the Earth because another asteroid or large object hit the moon, causing an explosion that then sent this hurling towards the Earth. And that's how we see it today. This is not brought back from the Apollo missions. This was something found on the Earth itself. As far as the seas of the moon are concerned, remember we talked about that could be mafic material, which is basalt or gabbro. We believe now that the moon had in its early life severe impacts by asteroids on the far side of the moon. And those impacts actually sent shockwave through the moon that caused volcanoes to erupt on the near side, the side that's always closer to us. And those volcanoes then produced a tremendous amount of lava that flooded the areas around it with basalt type material, just like what we see on basalts on the Earth in Hawaiian Islands. So the dark areas are caused from basalt, and the lighter highland areas are typically caused from sedimentary rock or the original moon's crust, which is made of silicate material. What about Mars? This is a picture taken of Mars from one of our telescopes. Here's a picture taken from one of the rovers on Mars, and this looks an awful lot like shale in the foreground. We're not exactly sure if the processes are the same as what forms shale on the Earth, but it looks very, very similar to shale. And the distance, you have all kinds of other rocks. Wouldn't it be amazing to study a rock from Mars? Well, we can. In much the same way that we have a rock from the moon, a large asteroid hit the moon, hurtling the debris in all directions, some of that hitting the Earth. The same thing happened to Mars. And we now have in the park's collection a Mars meteorite. This meteorite is known as a Shergotite Martian meteorite. It is primarily an igneous rock that is mafic or even ultramafic and is formed of basaltic and olivine pyric material. And this meteorite is something you can also let the public touch. But we know that this meteorite came from Mars because when we take a look at the isotopic signature of it, so this is taking a look at the various isotopes composed within the material of the meteorite itself, we can compare that to what rovers, such as the original first rovers on Mars, the Viking spacecraft, or more recent rovers, what they have measured in terms of the atmospheric composition, and there's almost a perfect match. Therefore, this is in fact a meteorite from Mars, and I think when the public touches it, they get quite a kick out of that. So that kind of brings us to the end of the presentation. Of course, people may or may not have questions, but I usually run off by saying that those who are here and touch the moon rock or the Mars rock, who knows, maybe some of those people will be the first to venture out towards the planets, land on the planets, and conduct field geology on worlds outside of our own. And that's basically it. That's how we end the presentation.